in the last lecture we derived the transfer function equation has a response ratio, beta becomes the ratio of omega by omega n, and zeta is the ratio of critical damping in percentage. Based on which it derived a simple relationship between the variance of the response to that of the variance of the force, but here we are showing the corresponding connectivity between the mean value of the response and mean value of the force, and we already know in stochastic process we are talking about realization of the force and the x value. So, Fy, F1, F2, F3, F1, F2 etc. small n or realization of f of x, they are the set of team of f of x, whereas x1, x2, xn or realization of the response. So, connecting these two is my transfer function. So, we also see from equation 14 that equation 14 implies that if the force function is a zero mean process, then the response will also remain as zero mean process. So, let us quickly get the details of the response spectrum and see how does it look like. Now, let us look at the autocovariance of the response. We already know that for m of 0 mx also remains 0, and we agree that f of t, especially in offshore structures, is a stationary process. So, based on these we can now write a new function which is f dash of t can simply be said as f of t minus m of f. I can always deduct the mean value. Now, fortunately in my problem, being the problem remains stationary, this may tend to 0 for a zero mean process. So, it is as same as this. So, in that situation, if x dash of t be the response of the load process f dash of t, then I can write x dash of t as integral minus infinity to plus infinity h of x of s f dash of t minus s ds. This is standard form we are writing the expression for the response. Now, substituting f dash of t as f of t minus m of f, same way I can write now this equation as 0 to infinity because the realization at the negative value becomes invalid for us. So, f of h of s f of t minus s ds, I am using this relationship here, minus zero to infinity h of fxs of mf ds which I can say this is nothing but x of t is x of t minus, this can be said as mean value of x, which I call as equation number 15. Now, for x dash of t be a zero mean process, f of t and f dash of t will have the same autocovariance. Now, using this statement now, the autocovariance can be simply given as xj of t, xj of t plus tau is expressed as 0 to infinity h of s1 of f j ts minus 1 ds1 is one part of corresponding to xj multiplied by 0 to infinity h of x s2 fj of, I think I will write it here, multiplied by 0 to infinity h of x s2 fj t plus tau minus s2, because I am looking for a time shift, minus s2 of ds2. So, I can rewrite this equation slightly by arranging the terms accordingly. So, now this becomes integral of infinity h of x s1 h of x s2 fj of t minus s1 fj of t plus tau minus s2 of ds1 ds2, which I call as equation number 16. So, fx s1 s2 fj. Now, we already know, I will remove this, the expected value of xt plus tau can be expressed simply as limit n tends to infinity 1 by n of summation of j to n x j n x t plus tau. This is a standard expression for finding the expected value of this at a difference of tau. Therefore, I am just using the same methodology for expressing equation 16 now. I should say double integral 0 to infinity h f x s1 h f x s2 limit n tends to 1 by n of summation of j to n summation of j to n f j t minus s1, I think I will write it here, f j t plus tau minus s2 ds1 ds2. So, rewriting this equation slightly in a different manner, double integral 0 infinity h of f x s1 h of f x s2 now this is nothing but expected value of f of t minus s1 and this is nothing but expected value of f of t plus tau minus s2 of ds1 ds2. These are the two domains of integration s1 and s2. Now, I slightly re-alter this equation saying 0 to infinity h of x s1 h of x s2, this I am replacing by saying covariance of the force with tau plus s1 minus s2 ds1 s2. I can write this because since f of t is stationary, since f of t is a stationary process, expected value of x of t plus tau will be independent of time. To be very specific, independent of t, not tau, tau will be there. Therefore, now I can write the autocorrelation function. Any questions here? So, I will rub this part, take away this. Now, I can write the autocorrelation function for this condition, sorry, the autocovariance of the response, which I call as Cx of tau, which will be same as the autocorrelation function R of, we call this as Rx of tau, because the process is zero. So I can now write Cx of tau is 0 to infinity, 0 to infinity, hfx s1 s2, hfx s1, hfx s2, Cf tau plus s1 minus s2 ds1 ds2. I call this equation number 17. Now we already know that the response spectrum is connecting between the force variance and the, let us say, if Sf omega, that is the forcing function, be the variance spectrum, of load, that is F here, F of t, and Sx omega be the variance spectrum of response x of t, then the variance of x of t is given by the Fourier transform of Cx of tau. You can do a Fourier transform of equation 17, I can get the time domain to frequency domain. So if I try to do that, I get simply xx omega, that is nothing but the variance of the response in the frequency domain is simply given by 1 by 2 pi of minus infinity to plus infinity of Cx of tau e to the power of minus I omega tau d tau. That is the standard expression for FFT from the time domain to frequency tracing. I call this equation number 18. Now I have equation for Cx tau from 17, substitute in 18 and expand this and see what happens. Okay. So I should say substituting Cx tau from 17 and expanding. So I can remove 17 anyway, because 17 we already have. I will remove this. I can retain this equation as it is, remaining I will remove. So substituting Cx tau from equation 17 we get, let us see what do we get. So Sx of omega is equal to, okay, Cx has hfx terms, I will take it out. Okay, let us do separate integral. This is h fx s1, h fx s2. There is an advantage of writing it like this. Then I say 1 by 2 pi of integral of minus to plus Cf of tau plus s1 minus s2 e to the power of minus I omega tau d tau, then ds1 ds2. Is that okay? Okay. Now let tau plus S1 minus S2 be theta. I substitute it here to be theta, the d theta will straight away be d tau, okay, differential. Hence, I will remove this. Sx of omega now can rewritten as 2 integral 0 to infinity separately hfx s1 0 to infinity hfx s2 1 by 2 pi minus 2 plus Cf of theta because T S1 S2 is theta. Now from this expression tau will be theta minus S1 plus S2. I have got minus sign here. So what I do is I take S1 separately, S2 separately and T separately. Let us see how we do that. So I need to have I omega tau. Tau is nothing but theta minus S1 plus S2, I separate it. So I want theta separately, I write that value here E minus I omega theta, theta is here with me. D theta I club it here because that is my integral here. Then I say E I omega S1 minus S2, is that okay? There is a minus sign. The minus sign, there is a minus sign attached to S1 which goes away, there is a plus sign at S2 with this minus becomes minus, is that all right? ds1 ds2. So now I can rewrite this equation slightly, rearrange it. Maybe I will write it, okay, I will write it here, which can be 0 to infinity h of fx s1 I have separate terms here, I am picking them separately, E I omega s1 of ds1 with second term of integral 0 to infinity h of x s2 E of minus I omega s2, I think I will, okay, no problem, ds2, and this term 1 by 2 pi of d theta. This can be simply, because this relates to the force, can be simply called as SF of omega, is it not? Okay, look at the equation back, it is SF of omega, right. Now I rewrite this last equation once again slightly in a different manner. Which can be now said as, I am talking about Sx omega, which can now be, this is Fx 0 to infinity, this is nothing but impulse response function, we already remember this, okay, small h is nothing but impulse response function. So I do for integration, I get this value as h of Fx of minus omega and other values h of Fx of plus omega, 2 values multiplied by SF of omega. Now, e to the power of minus omega star or any multiplier will have the same implication as ei omega or eix, let us say, not talk about omega, any value of star will have ix. Then I will remove this, h of hfx of minus omega can be written as this value, can be written as 0 to infinity of h of fx of t of ei omega t of dt, which can be also said as 0 to infinity of hfx of t e to the power of minus I omega star of dt. So, this can be written further as 0 to infinity of hfx of t of e I omega t dt and put a star here, which is as same as star. Therefore, I can write Sx omega as mod value of omega square of Sf omega. Okay. The equation number 90. Which gives the relationship between the response spectrum Ss omega to that of the force spectrum Sf omega or the load spectrum. So, equation 19 gives the relationship between the response spectrum Xx omega and the load spectrum F omega. But interestingly, equation 19 does not contain information about the phase lag. It gives only the amplitude of the magnet, amplification of the amplitude. Okay, amplitude amplification we can say. Now, let us see how does it look like for weak dampment systems, that is very important. So, let us try to plot this. Let us say I had a system subjected to some f of t subjected to some f of t. This is time and this is variation of amplitude of the force with respect to time. I impose this system, this force to a mathematical model having k, c and m having x of t with some force f of t. This is my f of t, this is my x. I have to measure x of t from the mass center, which gives me a response like this. Okay. If I try to plot the covariance function of this, it appears to me like this will be t, or now instead of c, t, because it is a stationary process, we put this as tau, and this becomes my Cf of tau, which we already had the equation. Correspondingly, I can also have the impulse response function, which can look like tau, which is hf(x) of tau. On the other hand, if you look at the response function x of t, then it plots like this. This can be Cx of tau. So, if you look at the load spectrum, it looks like this. Some load applied, let us say the content only we are looking at. So, this becomes omega and this becomes Sf of omega, looking only the energy content of the spectrum. And the transfer function which connects this spectrum to the response will look like this. Which I call h of fx omega absolute. For different omegas, of course, basically it will come to 0. Okay. And the response spectrum, after connecting the transfer function to the load spectrum, will look like this. So, we have very important information from this, very important information. Let us see what are they. We already know that mx is given by h fx0 of mf. This is what we have already derived, because you remember in stochastic dynamic analysis, unlike deterministic analysis in time domain, we do not look for the exact values of x of t, we look for the first order and second order moments of the statistical responses, realization of these values. So, the first order is the mean value we have here, which can be obtained from the transfer function, and already we just now saw the expression for the response spectrum, which is also said as the variance of the response. So, I am saying the variance of the response, that is the standard symbol, okay, is nothing but minus infinity to plus infinity of absolute value of h fx omega square of the transfer function of sf omega d omega. Okay. So, the square root of the variance will give me the standard deviation which we wanted for my analysis. The right hand side of this equation, I can call this both these equations as equation number 20. So, the right hand side of the equation of 20b, this is a and this is b, is evaluated numerically. Okay, it is evaluated numerically. Now, the question comes, if zeta is very low, you remember this function, this is having the zeta component into it. Okay. If the zeta is very low, what will happen to my response vector? Okay. Let us see that. Let us try to plot and write important inference from equation 20b and understand the quality of the response spectrum or the transfer function at very low zeta values, because we have zeta value only close to around 2% or maximum 5%. So, for zeta less than very less than 1, let us see how does it look like. The spectrum looks like this. We will try to plot the amplitude amplification given by h omega, that is plotted here, and of course here we plot beta, which is nothing but omega by omega n, and beta equals 1, that is at resonance. And these values are all written as, let us say, start from 0.1 by k, there is a denominator k in my h of omega. Okay. So, 1 by k, maybe 10 by k and 20 by k, 100 by k. So, 10 by k, let us say 100 by k. These are the values which I am trying to plot. For different zetas, all curves will start at 1 by k and it goes very steep and then comes down to 0. If you have zeta 0.1%, very low, I mean 1%, I will write zeta value not a percent, simply say it is 0.01. For any increased value of zeta, the curve will have this is for zeta of 0.1, this is for zeta of 1, this for zeta of, okay, it's 0.5 and 1, this is 0.5 and this is 1. So, we can write an interesting information from this curve saying for very low value zeta, h omega is closely amplified near omega resonance as a narrow band. Of course, for our clarity, h omega is given by 1 by k of root of 1 minus beta square square of 2 zeta beta square of E I minus I phi, is it not? Minus I phi in this equation or in this plot. So, the band is very close, the band is very close, okay. This is the band which we call as narrow band. Now, interestingly, in literature people call this aspect as white noise approximation. Let us see what is that white noise approximation. I will remove this. Now, we already know that sigma x square is given by minus 2 plus hf x omega square sf omega d omega for sf omega, that is the variance in the load, for sf omega varying slower than h of fx omega square, because you can see the variation is drastic here, okay. Then there is an approximation made in the literature saying that sf omega can be replaced by a constant called S naught. Where S naught is a constant. Therefore, sigma x square can be written as constant out minus integral to plus integral of the transfer function square d omega, and this is what we call as white noise approximation. What does it mean? The input spectrum is replaced by a constant, okay. That is called white noise approximation. So, we have a final inference from this statement saying the response spectrum to a large extent is determined by the square of the transfer function. Okay. So, some people write equation as response spectrum is equal to square of transfer function of that of the load spectrum or constant of this value. So, we have seen two important inferences. For the input load process remaining stationary, it amounts to a zero mean process where the transfer function becomes time independent. For a weakly damped systems, the amplitude amplification is focused, only near the resonance region. What does it mean? If you really wanted to control the response of any system of this order, you have got to only play not on a broadband system, only in a narrowband system. That is why generally in every case of response control algorithms, people tune the secondary frequency with the fundamental frequency of the system. That is the reason. One may ask why the response need not be controlled and tuned for the entire band of omega, it is not required actually. Okay, that is the reason why people do it. In fact, we have also seen one of the example which we solved on a TLP as well as on a tuned mass damper system on articulate tower, where we had tuned the secondary mass system omega with that of the fundamental frequency only. Of course, the benefit was looking like this. So, at practically omega equals omega n, it does not become 0, it is marginally 0, whereas you get two subsequent peaks. Okay. That is what we already seen in one of the case studies what we did in the last module in multi-leg articulate towers using tuned mass dampers. So, this is the reason why for weakly damped systems people look only the focus on narrow bands, and response spectrum in such cases essentially depends, highly dependent on the transfer function. Okay. So, in the next class we will talk about some important item called return period. What do you mean by return period? Because in stochastic dynamics, return period or what should be that period you must take for the load process is very important. We will talk about that, and we will also talk about modal response analysis. How many modes should I use? Where should I truncate my mode? Why and how? That will end the discussion on stochastic dynamics part. We will of course solve couple of problems, hand written problems, simple problems on modal analysis or modal participation factor. We will evaluate and see, because there has been questions from the students asking that how many frequencies or how many modes should I consider in a multi-degree freedom system model. We will address that in the coming lectures. Okay. So, any questions? So, the fundamental deviation of stochastic dynamics compared to the conventional deterministic analysis is that here we are not talking about the absolute values of the responses, we are talking in terms of its first and second order moments, mean and standard deviations, and of course variance and skewness also. So, based on this one can design the system further. Okay. That is what the deviation what we had from the conventional analysis what we did in the second module. Any questions? Okay.